Hi everyone, and welcome to lesson 2.3. So in lesson 2.1 and 2.2 we talked about solving systems of two lines by graphing and finding a point of intersection, and then we talked about how solutions to systems was the point of intersection of where the two graphs meet. In this lesson, we're going to learn how to find the points of intersection without actually graphing. So lesson 2.3 and 2.4 are two algebraic methods to solve systems, and the first method we're going to learn is called substitution. So after this lesson, you can solve for points of intersections of two graphs without graphing. In other words, you're going to be able to do this algebraically. Okay, so let's just get started. Maybe I should mention, in this case, we are going to, you're going to be able to substitute one equation into another, to obtain the POI. And I'm going to put in brackets S because sometimes there's more than one. Okay, so I'm about to show you how to do all the stuff that is written in this box, so please take a minute to read it. But I'm just going to get right into an example. So how do I solve using substitution? So let's just remind ourselves that we know this is a system because it has two equations and they're joined together by this curvy bracket. That curvy bracket associates this as a system. And we know that the solution to this system, so when I'm being asked to solve, okay, what I'm being asked to find is the points of intersection of these two, in this case, lines. So in order to do this algebraically, what I'm going to do is designate each of the equations using a number, so 1 and 2. And then what I want to do is I want to isolate one of the variables. And what we'll notice here is that we have the x's lined up, we have the y's lined up, we have the equal signs lined up, and then we have these constant terms lined up. So what I want to do is actually isolate either x or y in one of these equations and substitute it into the other equation. Now this sounds maybe a little bit complicated, but in this case there's a really obvious choice. The really obvious choice is this y. And the reason this is the obvious choice is because there's a coefficient of 1. Now, the reason a coefficient of 1 is important is because when I isolate it, so let's isolate y in equation 1. So we get 2x plus y equals 12. Well, since the coefficient of y is 1, I can just really easily isolate it. So I was able to isolate in one step, whereas if I chose, say, for example, negative 2y and isolated y there, I would have to divide by 2. So a good clue or a good rule of thumb is when I isolate a variable, I'm going to try to pick the one that has a coefficient of 1. So this is still technically equation 1. It's just rearranged. So now what I'm going to do is I'm going to substitute 1 into, and by the way, you can never substitute 1 back into 1. What you're going to do is substitute 1 into the unused equation. So we're going to sub it into 2, and we do it in the following way. Well, we know that 2 is 3x minus 2y equals 18. But what I'm going to do now is I'm going to take this y and I'm going to substitute what I got in equation 1. Okay, when I isolated y, I'm going to substitute that in for y in the second equation, hence the name substitution. So I get 3x minus 2, and I'm going to put brackets here because, of course, when I make this substitution, I have to make sure there are brackets around it. Next, I need to simplify. So what I'm going to do here is distribute the negative 2. And what you'll notice in this line is the only variable I have is x. So I can solve for it. So I'm going to get 7x equals 24 plus 18, 42. And I'm going to divide both sides by 7. I'm going to get x equals 6. Now, if I told you that the point of intersection here was x equals 6, well, you should be telling me that that doesn't make sense, right? Because a point is supposed to have coordinates x, y. So how do I go about finding the y value of the point of intersection? Well, I can just sub x equals 6 into, and I can sub it into either 1 or 2. I can just pick one. So, might as well just sub it into equation 1. So equation 1 is 2x plus y equals 12. So I'm going to sub that 6 in there. And I actually get that y equals 0. And that's okay. That's not a mistake. Okay, what that means is the point of intersection, and remember our answer should be what the point of intersection is. The point of intersection of this system is 6, 0. Remember, we write the answer in alphabetical order. Okay, now if I wanted to, I could go back here and check my answer. Maybe let's do that in red. So if I wanted to check that left-hand side equals right-hand side, what I can do with the first equation is I can sub in 6, 0. So 2 times 6 plus 0, does that equal 12? It does. In the second formula, I get 3 times 6 minus 2 times 0 equals 18. That also works. So I know I've done it correctly. So let me do one more with you. Okay, so for this one, I can actually see that it's much easier to isolate x in equation 1 than it is to isolate anything else in this system. So what I'm going to do is isolate x in equation 1. Okay, so I get x minus 3y equals 11, and I can rewrite equation 1 as 3y plus 11. And then what I'm going to do is sub 1 into 2. Again, we're never going to sub 1 back into 1. We always have to use the unused equation. Right, so now we know that y equals negative 3. I can sub this back into either 1 or 2. Let's see, so if we look at equation 1, we get x minus 3y equals 11. Let's sub in y equals negative 3. So I get x plus 9 equals 11. Therefore, x equals 2. All right, so here we go. The point of intersection is 2, negative 3. Now, if you recall, in a previous lesson, we talked about the different kinds of systems we could get. And if you remember, there were actually 3 kinds. There were intersecting, overlapping, and overlapping had infinitely many solutions. Intersecting has one solution, exactly one solution. Okay, and parallel is what we call the last type, and this type had no solution. So I'm going to go through these questions, and I'm going to do them, and we'll see that I've included examples of each type. So we just saw 2 examples of an intersecting system. Okay, so now what I want to do is I want to use substitution for this system. Now, when I look at it right now, I don't actually see any variables that has y by itself, But what I can see is that I can write these as equivalent systems. So if I take equation 1 and I divide all the terms by 2, I actually get 2x minus y plus 3 equals 0. And if I look at 2 and I also divide that by 2, I get 3y. Actually, I can divide by 3, can't I? I can divide by 6. Okay, I'm going to get y equals 2x plus 12. Okay, now if I look at, and I should be writing my brackets, so now if I look at equation 2, I can it already has y isolated, right? It has y equals 2x plus 2 there. So now I'm going to sub 2 into 1 to see what I get. So 1, and I'm going to write this version of it, 1 is 2x minus y plus 3 equals 0. I'm going to sub in y. Of course, I cannot forget my brackets. I'm going to get 2x minus 2x plus 15 equals 0. And guys, this is not a mistake. 2x minus 2x is 0. So actually, the solution to this equation is 15 equals 0. Now, how do I interpret that? Well, this is a really special outcome. If I look at this, 15 equals 0, well, that just is never true, right? It's not true. It's a false statement. This is never true. And that tells me that there is actually no solution to this system. So if it's algebraically, remember we said that the algebra and the graph have to go hand in hand. If algebraically it doesn't make sense, or if you get something that has no, is nonsensical or is never true, that means there is no solution to this system. And it's very important that you actually write the sentence down, because if you just leave it like that, I'm going to think that you're confused and you don't know the correct answer. But the correct answer is actually that there is no solution to the system. Now, is there a way we could have figured out that these were parallel parallel without actually doing all this work? Well, if I just write these so that all the x's and the y's and the equal signs were lined up, so in this case I would get negative 12x plus 6y equals 24. Yeah, I would be able to see that here, for this side of the equal sign, we know that there's a multiplier of negative 3. But if I look at this side, my multiplier is actually negative 4, which means that it has the same slope, but different y-intercept. And that's something we learned in a previous lesson. But really here, this is the most important part, that algebraically you get something that is never true. Okay, let's try one more. It looks almost exactly like number 3, but I'm sure it's a little bit different. Okay, so actually, we see that there's a coefficient of 1 in front of the x here. So let's isolate x in equation 1. So we get that x equals 3y minus 6. And we're going to sub 1 into 2. Okay, so here we go. I have 6y equals 2x plus 12. I'm going to sub in 3y minus 6 in for x. 6y equals 6y minus 12 plus 12. And again, this is not a mistake. Okay, what we end up getting is 0 equals 0. So it looks similar to the previous case, but actually we're in the other scenario where instead of it being never true, this is actually always true. Okay, and meaning that in this case there are so many solutions, in fact there are infinitely many solutions, that basically 0 equals 0 is an indication of that. So always true means that the system is overlapping. And actually, maybe we should just rewrite it. Okay, so I should put here also when it's never true, this is a parallel system. But we can check that out here again by lining up all the x's, y's, equal signs, and constants. Negative 2x plus 6y equals 12. We can pretty clearly see that all of these terms have a multiplier of negative 2. So therefore, it's the same line. And yes, it's overlapping. Now, remember, when we said that when a system was overlapping, we have to give 3 sample solutions. How do we do that? Well, since both of these lines are overlapping, what we need to do is we can pick one, let's say 1, and what I would do, I think the easiest thing to do, is to write it in the form y equals mx plus b. So I'm going to move the x to the other side, and the 6, and I'm going to divide by negative 3. And now I can just do a table of values. And we said that since there's a denominator of 3 on the x, okay, the best thing to do, well, we can always pick x equals 0, but we're going to want to have x values that are like multiples of 3. We can even throw negative 1 in there. So if I sub in 0 for x, I get 2. If I sub in 3 for x, I get 3. If I sub in 6 for x, well, this is 2 plus 2, I get 4. And let's just put in negative 3 as well. So negative 3 over 3, that's going to be negative 1 plus 2. So this is 1. So here I have actually 4 sample solutions. Okay, so what I do is I take equation 1 or 2, and I have to write it in the form of y equals mx plus b, and then just give 3 sample solutions. All right. So this is independent practice. I would like you guys to stop the video now and give it a try. Come back on once you've tried them, and you can check to see that your answers are correct. Good luck, guys.